Okay, so last week was the end of 6 weeks. You guys had sort of some makeup days to finish up anything from units 6 and 8 that you had not finished since it was the end of the 6 weeks. So I've disabled them now since the 6 weeks is over. So when you guys log into Canvas, you should only see this like admin orientation module. And then you should only see this current unit 9 module. I disabled everything else so that it wasn't kind of cluttered up right now. So for today, we're starting unit 9, which this unit focuses on solutions. So we're going to start out today with a couple of different things. The reason there's 2 things on here today is because I gave you guys 2 days last week to catch up and finish for the 6 weeks. We're having to kind of double up today just to make sure that we don't get too off track for the end of the year. So there's kind of 2 activities today. There's one on the water molecule and what we call polarity that we're going to go through. And then the second part, and it kind of relates to it, it's called electrolytes and non-electrolytes. And so we're going to learn like what are those terms and what is an electrolyte and a non-electrolyte and kind of what do they do and why are they important. Okay. So when you look at today's agenda, we're going to again talk about the structure of the water molecule, and we're going to talk specifically about what makes water unique, because obviously like we drink water, water's in our cells. It helps a lot of things function. It's also in the environment, like rivers and lakes and all that kind of stuff. It's in the oceans. And water is important because that's how we can have life on Earth. And so we're going to talk about like what is it that makes water unique? Because really, when you boil down to it, it's because of its chemical structure. It's because of the way that it's shaped in the molecule of the water, gives it all these special properties that other compounds don't have. And that's what makes water so unique and so important to life and to kind of just everything. And so we're going to talk about that structure of water. Then we're going to talk about solutions and how solutions form and how different things dissolve, because different substances, depending on what type of compound it is, like if it's an ionic compound or a covalent compound, they're going to dissolve in water differently. And so we're going to talk about the process for how those different types of things dissolve. Based on what type it is. And then based on if it's ionic or if it's polar covalent or non-polar covalent, we're going to talk about how that relates to the electrolytes and non-electrolytes thing and what those things mean. Okay, so down here on the agenda, just note that both of these are going to be for grades. So, you know, the second one, the electrolyte one, it's pretty short. It's not as long as the first one. So just make sure that you're working on both of them. If you don't get them both done by Friday, it's okay. You can catch up over the weekend if you need to. But I did want to make both of them available today just so that you guys know that we're kind of catching up since we had a couple of days where y'all had makeup days last week. All right, so the first part, we're going to talk again about water molecule and what we call polarity, because polarity determines whether something dissolves or not. And so this little animated GIF right here, these are just showing water molecules, and they're actually forming these little bonds between the molecules. So these little yellow and dotted black lines, okay? And so what happens is water molecules, they can form these little bonds in between water molecules, and that helps hold them together more so than other substances that have similar structure to water. Or similar masses to water molecules. And so this is what makes water unique, because it gives it like a really high boiling point. So it stays a liquid longer than a lot of substances that have small molar masses like water. And that's what allows it to be, you know, liquid on Earth for so many temperatures. So before we get started, I told you guys we're going to kind of review some bonding, because depending on if something is ionic or covalent, that determines how it's going to dissolve when you try to dissolve it in water. So this is kind of from last semester when we learned about the 2 types of compounds and how to like do their names and formulas and all that kind of stuff. And so just as a quick review, we have the 2 main types, ionic and covalent. So remember, an ionic is made up of usually a metal and a non-metal. The exception would be if it's one like this, where it has one of these polyatomic ions. So obviously this is a metal, and it's not one non-metal, it's a polyatomic ion where there's more than one non-metal, okay? But the basic formula is going to be a metal and a non-metal in the formula. The difference here for covalent, it's 2 non-metals. And so if you look at all of these, like hydrogen and oxygen, carbon and oxygen, nitrogen and hydrogen, all of those elements are non-metals on the periodic table. When we're talking about how they form the bond for ionic compounds, they're going to transfer electrons. The metal loses its valence electrons and it transfers, it gives them to the non-metal. And then you end up with a positive and negative charge that are attracted to each other, okay? And that holds the bond together for the compound. For covalent compounds, since they're both nonmetals, there's no metal to give away its electrons, so there's no transfer here. They just share electrons because both nonmetals want to gain, and since they both want to gain, they kind of compromise and they're like, well, we can share. Okay, so they form a bond by sharing electrons. And if they're non-polar, they don't really have any charge. If they're polar, then they have kind of one side of the molecule has a partial positive charge, the other side of the molecule has a partial negative charge. And so water is an example of a compound that is polar covalent, meaning that one side of it where the hydrogens are has a partial positive charge. The other side where the oxygen atom is partially negative. And that's what allows it to dissolve so many different substances, as we're going to see when we go through here today. So when you're going through this later on your own, there's some practice down here. It's got a little periodic table and it wants you to determine if the compounds it's going to give you to check are ionic or covalent. So you would kind of look at the formula and then you can use this periodic table as a guide. So it's got the metals and the non-metals color coded. And then obviously here in the middle, these ones are the metalloids that are right along that zigzag or that stair step line. So make sure that you go through and you check to make sure you're able to identify them correctly, because that's going to directly impact sort of if you're able to determine the dissolving things. So specifically looking at the water molecule, okay, it's held together by covalent bonds. So if I look at a water molecule, here's the hydrogen atom, here's the hydrogen atom, and here's the oxygen atom. And so what happens is the hydrogen and oxygen, they're going to share a pair of electrons between them and form a bond that way. What happens though is they're not sharing them equally, okay? Oxygen is on the periodic table, it has a higher electronegativity. And so that means it's kind of like oxygen stronger. So it's going to attract, it's going to pull the electrons towards it more so than the hydrogen. And so what happens is because they're not sharing them equally, it's kind of like tug of war and the oxygen's kind of winning. And so what ends up happening is they're still going to share, but in the bond, the electrons are closer to oxygen. So we label the oxygen atom as having a partial negative charge. And we do that by using this little Greek symbol. This just means that it's partial. It's not a full negative one. It's just a partial negative charge. And then each hydrogen atom gets labeled with the same symbol, but with a plus sign to indicate that the side of the molecule where those two hydrogen atoms are, that's partially positive. And that's important that we know that the oxygen is partially negative and the hydrogens are partially positive, because that is what allows water molecules to kind of interact with each other. Because what happens is when you get a lot of water molecules together close to each other, they're going to sort of line up to where the hydrogen atom on one water molecule is going to be lined up near the oxygen on another one, because that partial positive from the hydrogen on one water molecule, it's going to be attracted to the partial negative charge on another water molecule. And so that's what we call, it's called a hydrogen bond. Okay, so what happens is, see, here's this, the red is always oxygen and the whites are always hydrogen. When you see water molecules, they look like little Mickey Mouse heads. Okay, and so here, this side where the oxygen is, this would be a partial negative area, and it's going to be attracted to this hydrogen that's partially positive. And that usually this is represented by a dashed or a dotted line, because it's not a full bond. It's not like an ionic bond or a covalent bond where there's things, you know, transferring or sharing electrons and it forms a permanent bond. It's sort of a temporary bond, okay? Because this is why water flows, is because the hydrogen bonds are kind of like they're forming and then they're breaking, they're forming and then they're breaking. Now, when you cool the water down low enough, the hydrogen bonds will kind of lock in place, and that's when you get ice, okay? But so all these little dashed lines, and you can see that it's always like, here's an oxygen and it's attracted to this hydrogen on this one. This hydrogen is attracted to this oxygen. So they sort of arrange themselves because the charges, those partial charges exist, okay? One thing that this really is important in, and this is something that you guys learned about last year in biology, is DNA. So in DNA, there are a lot of hydrogen bonds because you have the bases like the AT and the GC, and they are attracted by hydrogen bonds. And so all of these other bonds, these are all covalent bonds, because all of the things in DNA they're all nonmetals. But that what actually holds that double helix together, what goes in between those base pairs, you know, the AT or the GC, these little kind of red dashed lines, those are hydrogen bonds. And so hydrogen bonds pretty important because it helps keep those bases together, and it provides that double helix structure that like we know DNA for. And if hydrogen bonds, you know, didn't exist, then DNA wouldn't hold together, and who knows what we would be. Okay. So I mentioned polar and nonpolar. So water is really going to be a big focus for us because water is usually what we use to dissolve compounds on Earth, because it's called the universal solvent. It can dissolve a lot of different things, but it's not the only covalent compound that has that unequal sharing. Anything that has that partial positive negative charge, those are all called polar molecules. Now, when they share things equally, they're called nonpolar. And so these are just some examples. If you look over here, so if you have two of the same atom bonded to itself, like this is just nitrogen gas N2, that's going to be nonpolar automatically because it's the same atom. And so they're going to have the same electronegativity or the same strength. So they're going to share equally. For other elements, what you would have to do is you would have to figure out if the elements, or you'd have to look up the electronegativities of the elements, and then you'd have to kind of look at each bond individually. So I could look at this CO bond and this CO bond, and then based on, you know, sort of the numbers, I can determine that it's like symmetrical. It doesn't have any lone pairs on its Lewis structure, and so it's going to be nonpolar. Okay. Same thing for the CCl4 down here. Now these over here, all of these are examples of polar molecules. So HCl, because hydrogen has a lower electronegativity than chlorine, and so the electrons here are going to be closer to chlorine in this bond. Water, we've already seen, the oxygen side is the partially negative, the hydrogens are the partially positive side. And then another really common one is NH3, which is ammonia. This nitrogen is the partially negative area, and then the hydrogens are each partially positive. Okay. So what happens when I try to dissolve something that's an ionic compound in water? Okay. So water dissolves a lot of substances. It can dissolve any polar covalent compound, and it can dissolve most ionic compounds. Okay. There are going to be a few exceptions that it can't dissolve, and we're going to get more into that on Friday, because we're going to learn how do we tell if something will or won't dissolve based on the elements that are in the compound. But for the most part, what happens when you have an ionic compound like NaCl, which is table salt, what happens is you have the positive and negative ions, and when you dissolve it in water, it looks like the salt disappears, but what's really happening is it's being solvated. And so what's happening is the water molecules are surrounding the positive ion and the negative ion. And what happens is, if you notice, this side here, the red side, is the oxygen side that has the partial negative charge. It lines up with that positive ion. On the other side, this negative ion, it lines up where the hydrogens are going to be facing it. And so when you have a negative ion, it's going to be surrounded by water molecules with the kind of like the Mickey Mouse ears facing inward, because the hydrogens with the partial positive charge are attracted to it. But the positive ion, which in this one is the sodium, it's going to be surrounded where sort of like the Mickey Mouse head is going to be facing inside, not the ears, because that partially negative oxygen is going to be attracted to the sodium. And usually they're going to be surrounded by I believe it's 6 water molecules. There's a ratio. I think it's 6. And so what happens is the water molecules pull apart these ions. So when you dissolve an ionic compound like salt in water, there's not NaCl floating around. There are positive sodium ions and there are negative chloride ions. And so one kind of property of ionic compounds is that when you dissolve them in water, they all conduct electricity, okay? Because there's going to be those negative and positive ions floating around in solution. When you dissolve covalent compounds, they do not split apart because they don't have ions. And so they don't conduct electricity. So there's a little video below that shows a little animation of, like, I've taken kind of like a cube or a chunk of salt, and I'm dissolving it in water. And so when you watch it, you're going to see that what's going to happen is the water molecules are going to pull the positive and negative ions apart, and they're going to surround it, kind of like this one you can see that's starting right here. And so that's what happens when you dissolve something that is ionic, is that it has positive and negative ions that split apart, and they're surrounded by those water molecules. Now, on the other hand, polar covalent compounds, they're not ionic, so they don't break apart, but they are still able to dissolve, because since they're polar, they have that partial negative and positive charge on the molecule. So the water molecules can still be attracted to them. And so they don't get broken into ions or atoms. When you mix, what happens is the water molecules, they'll just surround the whole entire compound, and they'll kind of attach to it wherever the partial charges allow them to be attracted. So this is actually showing sugar, which is the chemical name for table sugar. It's sucrose. And so it's C12H22O11. So it has 12 carbon atoms, it has 22 hydrogens and 11 oxygens. And so it's kind of a big molecule. And so what happens is you'll have a lot of water molecules that will surround it, and they'll be attracted to wherever parts or whatever ends allow it to that have that partial negative or positive charge. So there's another little video here where it's going to show you kind of dissolving some sugar. So the difference here is that sugar, if you dissolve sugar in water, because sugar is polar covalent, it will not conduct electricity. So sugar water won't conduct electricity. Salt water will, because salt water is going to be an ionic compound dissolved in water. Now, the last thing is nonpolar covalent. So nonpolar covalent, they will not mix or dissolve in water. And the reason is because there's no partial negative or positive charge for the water molecule to surround and be attracted to. Okay. So since it's unable to attract them and it can't connect to anything nonpolar, it can't mix and dissolve. And so the biggest examples are going to be any kind of oils and fats. So like olive oil, vegetable oil, canola oil, you know, like grease or like fat from like cooking meat and things like that. And then another big one is this compound called ethane. So things like gasoline, they're going to be, you know, in this category as well. And so typically what happens is you'll usually see oil floating on top of water. The reason the oil floats is because it's less dense. The water has a higher density, so it's on the bottom. And so there's kind of a phrase that we use to dissolve to kind of describe this. It's called like dissolves like. So what that means is if things are alike, they will dissolve together and mix together. So for water, since it's polar and it has those partial and positive and negative charge, it will dissolve other polar covalent substances like sugar. And it will also dissolve ionic compounds since there's a positive and negative charge there. It will not dissolve anything nonpolar. Okay. Now that's not to say you can't dissolve something with oil, because if you have two different oils and you mix them together, they're going to dissolve and mix together because they're both nonpolar. Okay. But for most solutions, we focus on water. And so that's why usually we say, you know, water's not going to dissolve anything nonpolar. Okay. Now, one interesting kind of, I guess, real world application of this right now is the coronavirus. The coronavirus molecule, it's actually surrounded on the outside of it, it's surrounded by a shell of, or a layer of lipids, which are fats, if you guys remember from biology. And fats or lipids, like oils, those are all nonpolar. So fats and lipids are all nonpolar. And so water cannot dissolve those nonpolar things like we just looked at right here with the oil. And so that's why when they tell you guys to wash your hands, they're like, make sure you use soap and not just water, because water alone will not it won't destroy or won't get rid of the coronavirus, like off your skin or off your hands or whatever. But what happens is when you use soap is a special kind of molecule called a surfactant. And one end of the soap molecule is polar and the other end of it is nonpolar. And so because of that, it kind of acts like a go-between, because the soap is going to be attracted to the water molecules that are polar. It's also going to be attracted to any kind of oils or lipids that are nonpolar. So it's the same concept for like why you have to use soap to like wash dishes, okay, and things at home, because the soap is going to allow the water to sort of get in and clean any kind of grease or oil off of like dishes or off your skin. And so same concept for the coronavirus molecule. They tell you to use soap and water because using the soap allows the water to get in and sort of get all the coronavirus off of your skin. So at the very end here, when you guys are on your asynchronous time, the very last page on that is going to be sort of a practice, not a quiz, but some practice questions. I clicked on the wrong thing. Let me go back. And I just wanted to reiterate to make sure when you get to the very end, after you make sure you go through and answer all the practice questions, watch the videos, and do all the different parts that are on each page in the little book here, that when you get to page 8, make sure that you submit the report, okay? So make sure that as you go through, that wherever there were questions, you complete the questions. And that you watch any videos and things like that. Okay. All right. So then the second one today is going to kind of take the whole polar non-polar thing, and we're going to apply it to this concept of electrolytes and non-electrolytes. Okay. So electrolytes are substances that will conduct electricity in water. So if you watch this little image or this little GIF, what happens is they have that thing in one substance and it's not conducting electricity, and the other one, they dip it in the other one and it conducts electricity. So it completes the circuit and the light bulb shines. Because you can, if as long as there's moving ions and something that will conduct electricity to complete the circuit, the light bulb will light up. And so non-electrolytes can't conduct electricity when you dissolve them in water. And so there are some terms here just to review. When you have a solution, there's two main components. So the solute and the solvent. Okay, typically the solute is usually a solid substance. It can be a gas or liquid, but majority of them are going to be solids like sugar and salt and things like that. Your solvent is usually a liquid. Most often for our solutions, we're going to be using water. Okay, they're going to be called aqueous solutions. But there are other things that can be solvents. And then the solution is what happens when you dissolve it and it comes together. Okay. Now, electrolytes and non-electrolytes, these are kind of two categories that we can kind of sort solutions into. And so electrolytes are a substance that when you dissolve it, it splits into ions. Okay. That's going to allow it to conduct electricity. A non-electrolyte is something that when you dissolve it, it does not split into ions. So thinking back to what we just talked about with the basic solution stuff, electrolytes are going to be ionic compounds, because we just talked about that when ionic compounds dissolve, those are the ones that split into the positive and the negative ions. Non-electrolytes are going to be the polar covalent substances. So they dissolve, but they do not split into ions when you dissolve them. So it's like sugar. Okay. And so right here, it kind of reiterates substances whose aqueous solutions are conductors of electricity. Those are electrolytes. If they don't conduct electricity, they're non-electrolytes. Okay. This is kind of a little image. So this one on the left, this is showing an electrolyte dissolved in water. So notice that there are kind of 3 positive ions and 3 negative ions. So we took some ionic compound like salt, like table salt, NaCl, we dissolve it in water and it splits apart into those sodium ions and chlorine ions. And because those positive and negative charges exist, it can conduct electricity. So ionic compounds are electrolytes. Those are related to each other. Non-electrolytes are going to be your covalent compounds. Specifically, it'll be the polar covalent, because it can dissolve in water, but it can't conduct electricity. Okay. And so since there's no separate positive and negative charges, they don't conduct electricity. Okay. So down here it has some practice. It says which would most likely be an electrolyte. So based on what we just talked about, if you want to know which is the electrolyte, you need to identify which is the ionic compound. So it might help you to go back to that first lesson and kind of look at the periodic table at the very beginning to help identify if things are ionic or covalent. So then we kind of go a little further. So electrolytes, they conduct electricity, but we can kind of even categorize them a little more. We can call them strong electrolytes or weak electrolytes. Strong electrolytes are going to dissociate or split into ions completely. So that means every single molecule splits apart into positive and negative ions. And because there are a lot of positive and negative ions, because they all split apart, it conducts electricity really well. So it would make like a really bright light bulb. Okay. A weak electrolyte, on the other hand, only part of the compound splits into ions. So, maybe only like 20% of them split into ions, or 10% or 40%. Okay. But it's not all of it. And so because there are not as many positive and negative ions floating around, it will conduct electricity because it has some ions, but it won't conduct it as well as a strong electrolyte. So a lot of times you'll see if they test that light bulb thing, like on the first page, if the light bulb is really, really bright, then that's going to be an indicator that would be a strong electrolyte. If the light bulb kind of lights up, but it's kind of dim and not as bright, then you would probably conclude that you would have a weak electrolyte, because it is conducting electricity, just not very well, and your light bulb's not very bright. Okay. And this is just kind of summarizing what I just said about conducting electricity and having a few free ions or a lot of free ions. And so here's another image. So this one here on the left, this one's showing a strong electrolyte. So notice it looks like we had 4 ionic particles, and they all 4 broke apart, because I see 4 negative, the green ones, and I see 4 positives, the red ones. So all of them split apart. They can all conduct electricity. This one on the right, this one is weak, because if you look, only one ion of the compound split apart. So here's one that here's the positive and negative split apart. The other three, they stayed together. They did not dissociate or they did not ionize. So if you see the word dissociate or the word ionize, that means to split apart into ions. So this one on the left did not fully ionize or did not fully dissociate. So it can conduct electricity because it does have this one that split apart, but it's not going to conduct it as well. And so this little image is kind of showing what I was talking about. This one here, if you click on it, this is showing a non-electrolyte because they've put they've hooked up, you know, a light bulb and an electricity source. And so because none of these are split apart, there's no way to carry the charge from this negative to this positive end. So the circuit's not complete and the light bulb does not light up. Now here in the center, this is a strong electrolyte. If you look, all of these are separated. They're all pluses and minuses separated. So all of them can carry the charge between these plates here, and it completes the circuit and the light bulb lights up and it's very bright. On this one, there's only one that split apart. The other two didn't split apart. So it still conducts electricity because it's still going to complete the circuit. It's just not going to carry the charge as well. And so the light bulb is going to be dimmer. Okay. And it kind of tells you the example. So this is ethanol, which is a type of alcohol. This is potassium chloride. So it's an ionic compound. Those are usually going to be your strong electrolytes. And then your weak electrolytes are usually going to be weak acids. And so acetic acid is an example of something that would be a weak electrolyte. And when we get into our last unit, unit 10, you're going to have a lesson where you're going to talk more specifically about weak and strong acids and how they're sort of unique from just regular weak and strong electrolytes. So there's a practice down here. You can just, this is just based on, you know, the images, so you should make sure that you understand what each term means. So you can kind of drag and drop it and check yourself. And then this last thing is sort of, you're going to kind of see based on the three categories that were in the lesson, can you kind of match all of these things? So some of them are descriptions, some of them are actual compounds. And then there's the ones with the images of what the molecules and the ions look like. And so you'll just kind of drag and, you know, put them, you know, wherever you want to put them. And then you can check it and make sure that you have it right. This is good. This little table would be good to like copy into your notes, because this table is going to have a good summary where you'll have kind of the definitions, the examples, what they look like visually. And so that's kind of a good thing to have for reference. And then when you get to the last page, make sure that you submit your report so that the grade goes through to the grade book. Okay. And you can check before you submit that you've done all the questions and all the parts and all the different things. So that is it for today. So the first one, there's a lot of information, but not as many questions to answer. The second one, there's more questions to answer. But just make sure that both of them, you do both of them because they are separate grades. So these are going to be the first 2 grades for the 6 weeks. Okay. And then the recording will be posted later today if you need to go back and kind of rewatch anything we just talked about together or anything like that.